Canterbury. He's sort of the physical volcanologist of the team. Chad Deering and at Michigan Tech and Darren started this project ages ago, and the first time that they sampled the units I'll be talking about is in 2007. So this has been a project that's been in the work for quite a while. Another person I need to thank is Mark Garoso at OFM Research, who is a thermodynamics guru and has helped immensely with the rhyolite melts work that I'll be presenting today. And I can't start a talk without thanking my collaborators at Vanderbilt University, Calvin Miller and Gil Gualda. All right, so today I'll be talking about pre-eruptive conditions of magmas in the crust. Over the last decades, there's been a huge revolution in how we think about magmas in the crust and how we think about these magmatic systems and magmatic bodies that lead to large eruptions and lead to supereruptions. Here are just a few examples from papers over the last couple of decades that have really sort of put in perspective what we think about magmas in the crust prior to large ignimbrite forming eruptions. And why do we care? These are huge supereruption systems I'll be talking about, and they have huge implications for climate, they have implications for society, and their deposits go a really long way. We are also thinking about things through time. Here are a few papers by Cooper and Kent, and then Gualda and Sutton, looking at sort of the different time scales that we're concerned about here. In the top, we're looking at strontium and plagioclase, showing a fairly long, sort of a protracted history, but with blips of time where there's a high melt fraction in the crust. And then again, we're looking at things that go from the order of hundreds of thousands of years when we're looking at zircons, down to the order of less than a year when looking at quartz. So these are long-lived time scales, but they have different time scales that we're looking at. And today for the talk, I'll be looking at the sort of intermediate time scale when we're looking at crystal pore eruptive systems. So the pre-eruptive conditions I'll be looking at, a few of the things I'm interested in are the distribution of the magma in the crust. And so for distribution, I'm looking to see if magma is stored at different levels, if it's stored at the same level, how many magma bodies are there, things like that. For the temporal progression of magma in the crust, I want to know if there's some sort of change in conditions through time, if magma bodies change through time, if there's a shallowing, a deepening, a consistent type of pressure, all these types of questions about magmas through time. So the main questions that I'll be addressing today and in my PhD are how many magma bodies exist prior to large eruptions and how big are these magma bodies? What are the storage depths of the magma bodies? And how do the number and depths of magma bodies change through the life cycle of a large magmatic system? I know we get caught up in nomenclature, so for today, I'm thinking about magma bodies as individual magma types and individual bodies, and then the magma system, I'm thinking on a more reservoir scale, just to keep the names consistent. All right, and so the way that I do this is by using major and trace element glass geochemistry. That can help fingerprint different magmas and different magma types. And another way is via glass geobarometry, and that can help give storage pressures. For the temporal progression part of this talk, field relationships and tephras stratigraphy help us determine magmas through time. All right, so where we'll be going to the Taupo Volcanic Zone in New Zealand. You know, they probably have it a little bit better than we do today. They're just about to go into summer, and I would be, just love to be doing some field work there right now, but I'll just be talking about it today. So the Taupo Volcanic Zone is a highly active silicic system, and it went through an ignimbrite flare-up period from 350 to 280,000 years ago. And there were some fairly large eruptions, fairly large caldera-forming eruptions during that time. There are approximately 8. And you can see down here on the bottom right that they are sort of on the order of 50 to 150 cubic kilometers, with a major exception of the Whakamaru ignimbrite, which was the first of the flare-up eruptions and erupted over 2,000 cubic kilometers of magma during its time. So the Whakamaru I've highlighted here with the caldera right in the middle, or right just north of Lake Taupo. And it was, as I said, greater than 2,000 cubic kilometers of magma erupted, and erupted somewhere between 350 and 340,000 years ago. It's unusual in the TVZ in that it is fairly crystal rich with sort of 10 to 40 weight% crystals. The other typical flare-up eruptions have on the order of 5 to 10 weight% crystals. And I say here it's a complex eruptive system because there's a multiple ignimbrites that went both to the west and to the east of the main sort of central volcanic zone. And unfortunately, they have many different names and different eruptive episodes, and it's very challenging to get them in sort of a temporal stratigraphic context. There are also different types of magma that have been documented here. Brown's work here described 4 different types of magma, A, B, C, and D. But unfortunately, it's still very challenging to see which ignimbrite produced which magma type. There's also been work on some tephra in the Bay of Plenty, which is just to the north of the Taupo Volcanic Zone along the coast. And this is work done by Manning that helps use the tephras erupted from the Taupo Volcanic Zone in order to sort of give a context, give sort of a temporal signature to them. So I'll be using, so I would love to be using the ignimbrites and will be using them in the future. But really, in order to determine how things change through time, we need to look at the tephras. So that's what I'm going to be doing here. So the Whakamaru tephras are really the key to the eruptions through time. Here for Whakamaru, the distal tephras were found greater than 2,500 kilometers from the source. And you can see here for context, the Chatham Island is about 850 kilometers from the caldera here. And so here we're looking at the tephras just not quite that far away, but only 50 kilometers to the northeast of the caldera. We're looking at 2 sections near Whakatane and Marata. And these were described by Manning. And they really illuminate the temporal progression of the magmas. Manning, in his thesis in 1995, just did a fantastic work going along the Bay of Plenty and documenting the tephra stratigraphy of all these different eruptions. It's quite an amazing thesis if you have some spare time. He correlated the Kohuawa tephras. These tephras called the Kohuawa. He correlated those to the Whakamaru ignimbrites. And so we're looking at the eruptions for the Whakamaru system, as well as both before and after the actual Whakamaru eruptions. And here the focus is on the pre-eruptive storage conditions of the magmas that produce the Whakamaru ignimbrites. And again, just for emphasis, we would like to use the ignimbrites, but really the tephras are the key to understanding things through time. All right, so this is one of the sections that I looked at. I looked at 2 different sections, and I'll just go through the different units that I'm looking at. First, I'd like to point out that there are some paleosols, which Manning documented and are actually fairly clear in the field, and they represent fairly long time breaks. And so this is a way that we can sort of determine sort of a longer time break between eruptions. The units we'll be talking about today are the pre-Pyrata tephras, the Pyrata tephras, the Kohuawa tephras, and the Murapara Banish tephras. And I know that the names, a lot of these Toroa Maori names are quite difficult at first, so I'll try to go through them a little bit slowly. So for the pre-Pyrata and Pyrata tephras, these are both known to be pre-Whakamaru ignimbrites, but the correlation to the actual Whakamaru magmatic system is unclear. The Kohuawa tephras are correlative to the Whakamaru ignimbrites, and so therefore are part of the Whakamaru magmatic system. And the Murapara Banish tephras are post-Whakamaru and then are also before the next ignimbrite from the ignimbrite flare-up period. And these are not Whakamaru magmatic system. All right, so for the methods that I used, we vertically sampled lapilli through the horizons and through the tephra deposits. We selected horizons for sampling. There were 22 sampled at one location and 8 at a second location. These different horizons that we sampled were based on, say, a change in grain size or just before and after paleosols. So we tried to get sort of the different parts of the eruption. So if something looked like it changed, we collected about 1 kilogram of tephra material. And we examined the mineralogy of several horizons, but not of each lapillus. We then picked 5 to 6 lapilli per unit. We did major and trace element glass geochemistry for each lapillus. The major element geochemistry was done using the SEM EDS, and the trace elements using LA ICP-MS. And then we also ran rhyolite melts geobarometry and zircon saturation geothermometry on each of the lapilli. In order to, and this I should show you, this is actually one of the sections on the left, this big picture. And this section here is a paleosol, which is the largest paleosol of the study. And here we have the Pyrata and into the Kohuawa. And I think this picture really illustrates, I love sampling here. It's just like the beauty of the different tephra deposits. You can also see the changes even just looking here. All right, so this is what my lapilli looked like. So here are 7 different lapilli here, and each bar here represents 500 micrometers across. So these are fairly small samples, and I'd like to emphasize that that they're so small that you really can't do mineralogy on individual lapilli. You have to do them basically by horizon. One thing to note is that all the data I'll be presenting is based on the glass. And so the glass represents the liquid that's in equilibrium with the crystallizing mineral assemblage. So it represents the pre-eruptive melt. For each lapillus, we chose at least 15 points to do both major and trace element analyses. The results were compared to USGS RGM1 standard in the SEM. And the analytical errors that I'll show for the individual analyses are smaller or similar to the symbol size. So we have fairly small errors on those. And we measured a fused RGM1 standard at least daily to monitor data quality. And for all the data I'll be showing the means and the standard deviation of the lapilli. Oh, and one other thing to mention is that the major and trace elements used are independent methods. And so you know, they're complementary because they're used on the same lapillus, but they are used for different things. All right, so are you ready for the major elements? Let's do it. All right, so with the major elements, I'd like to try to find differences in magma groups. So this is a calcium versus silica graph. And for the rest of the presentation, the pre-pyrrhota is in gray, the pyrrhota in blue, Kohiawa tephra in green and yellow, and the Mura Parabonish tephra in pink and purple. And one thing to note here is that all magmas are high silica rhyolites. You see here that we go basically from a little bit less than 76.5 up until just a hair under, I think it's 77.8 or 77.9 weight percent silica. And so they're all high silica rhyolites. Each point here represents one lapillus, and the error bars represent the standard deviation of the glass data. So for the pre-pyrrhota, I'll just walk you through this graph. The pre-pyrrhota, we only sampled 1 unit of it, and it seems fairly clustered and sort of seems like one magma type here. The pyrrhota overlaps pretty much right on top of the pre-pyrrhota tephra. What is slightly different from the Kohiawa tephras, and here I split the Kohiawa into the green and the yellow, and so it looks like there are likely 2 magma groups of Kohiawa tephra, and then the Mura Parabonish. The purple Mura Parabonish seems to overlap the green here in calcium silica space, and then the pink is slightly more disparate and has a slightly larger range. And this is also compared to distal tephras that are distal tephras that are correlative to the Kohiawa tephras, as well as Whakamaru ignimbrite data. The distal tephra data is from Matthews 2012, and the Whakamaru ignimbrite data is from Gualda et al. Ooh, that should be 2018, not 2008. Sorry, just a decade younger. And so you see here that the distal tephra overlaps mostly the Kohiawa green, and the ignimbrite data overlaps mostly the Kohiawa yellow. And so really using sort of the more proximal tephras, we can hopefully try to link the ignimbrite data to the distal tephra data. However, I think here we have a few different other major elements, and calcium versus silica here, iron versus silica, and magnesium versus silica. And again, potassium versus silica. And notice here that they're still all high silica rhyolites. Some magma groups are distinguishable in some oxides for major element compositions, but if you were sitting there and thinking, oh, I'm really not sure about splitting this yellow and these green, I agree. I also think that they are somewhat difficult to distinguish. And their groups are entirely undistinguishable or indistinguishable in silica space. Here, the major elements vary by sort of tens of weight percent, if that. And so what we want to do is to look at the trace element compositions in order to really try to distinguish the major elements, or excuse me, to distinguish the magma groups. All right, so now we'll go from major element glass geochemistry to trace element glass geochemistry. And here things become much clearer. Here we have rubidium versus strontium, europium star over barium, and zirconium versus europium. And here we start to see these different, cesium versus neodymium. And here we start to see these different groups pop out a little bit more. In the trace element, things can vary by tens to hundreds of parts per million, and in barium, up to 1,000 parts per million. And so here the groups become much more easily distinguishable. And so now the yellows and the green Kohiawa magmas become more distinct. So I'd like to say with both the major element and then confirmed by the trace element data, that we have at least 2 magma bodies that fed the Whakamaru eruptions. This is the Kohiawa yellow and the Kohiawa green. They're distinguishable in both major and trace element compositions. However, they're much more easily distinguished in trace element compositions. And another important thing to note is that they're geochemically distinct from pre-Whakamaru and post-Whakamaru eruptions. I didn't belabor on that point in the earlier graphs, but notice here that the both the pre-Whakamaru and the post-Whakamaru are quite distinct in trace elements. And here, so here, this is my sort of my building of diagram. We have the Kohiawa yellow and Kohiawa green. Yellow is higher in rubidium, cesium, and neodymium. The green is higher in calcium, strontium, zirconium, and europium star. So now I'm going to move into the rare earth. I'll let you guys look at that for another second. Sorry, I tend to switch sides quickly. Okay, so now we'll jump into the rare earth element glass geochemistry, and this is all chondrite normalized. Don't worry, you won't have to interpret this crazy plot. This is just to show you all of the data. So this is all of my rare earth element data. And so now to look at the Kohiawa tephra, we have both the green and the yellow tephras that seem to have different signatures in rare earth elements as well. So here for the Kohiawa yellow, we have a higher europium anomaly. And they're also more elevated in the middle rare earths and high rare earths. Contrast that to the green Kohiawa tephra. It's a much smaller, much smaller europium anomaly, and then the middle rare earths and high rare earths are slightly lower. And I'll show those overlapping one another again, so you can see that they are 2 distinct magma types. And the Kohiawa yellow has lower europium or higher europium anomaly, and is also higher in middle rare earths and high rare earths. And this is indicative of feldspar crystallization. And so really, not only can we determine a difference in magma bodies, but we start being able to have different interpretations of crystallization history. So this is indicative of feldspar crystallization. Oh, excuse me. All right. Another thing that we did just to confirm the difference between the magma bodies is to look at zircon saturation temperature. And so here you see, again, the green and the yellow are quite distinct. And as well, you can still see that the pre and post Whakamaru magmas are distinct here as well. And so the difference in zircon saturation is apparent as well for the different magmas. And just for the zircon saturation temperature, the temperatures are minimum estimates if magmas are zircon undersaturated, and they are the temperature estimate if zircon is saturated. We're not sure if zircon is saturated in these magmas, but we do expect that the yellow Kohiawa magma should have sanidine from europium star, and from barium. And so these are now starting to become a few not only geochemical signatures, but also like petrological implications from the geochemistry that we can use to start sort of signaling these different magma bodies. And so yeah, so I still want to know, can we further distinguish these different magma bodies? And as I said before, we're confirming now that we do have at least 2 magma bodies that fed the Whakamaru eruptions. The Kohiawa yellow likely contains sanidine. The Kohiawa green likely does not contain sanidine. And I should pause here to mention that that the Whakamaru in general is known to be anomalous within the Taupo Volcanic Zone for its presence of sanidine. However, I'm now showing that really only one of the magma types likely has sanidine, and so sort of one of the main distinguishers of the Whakamaru becomes slightly more murky. And so now I want to know, how do these magma bodies change through time? So what is their temporal progression? All right, so magmas through time. So now what I'm doing is not just showing sort of a bivariate plot, but also showing this through time. So this is horizon, and so this is the order of the different magmas. At the bottom we have the pre-Pyrata, the Pyrata, the Kohiawa tephras, and then the Murupara Banish tephra. And so this is sort of relative time. They aren't, although this graph might be slightly misleading because they look like they're evenly spaced, they're not quite evenly spaced, but this does give a relative time component. And these orange dashed lines are paleosols, which indicate longer time breaks. And note that there is no longer time break in the Kohiawa tephra sequence. One thing to note, probably the main thing to note here, which I think is super cool, one of my more exciting sort of aha moments, is that the Kohiawa tephras seem to have both magma types erupting throughout the entire sequence. And so it's not going between one magma type and the other. It seems to be consistently erupting both magma types. Another thing to note is that there are quite distinct changes both just going into the Kohiawa and coming out of the Kohiawa. So just pre-Whakamaru and post-Whakamaru, there are quite distinct geochemical changes in the magma bodies. And you can see this magma through time through a lot of different, through most of the different geochemical signatures. We have over here calcium and magnesium, two of the major elements, and you have zirconium, barium, and strontium over here. One thing that I think you might be able to like further distinguish magma groups is if you notice in the barium and the strontium, these sort of the latest erupted Kohiawa magmas have a slight decrease in barium and a slight decrease in strontium. So I'm wondering if there might be some slight difference towards the end of the Kohiawa magmas, but that's sort of the next talk. Okay, so the magma story through time now, building on that, is that confirmed two magma bodies fed the Whakamaru eruptions. Both magma bodies erupted throughout the Whakamaru eruptions. There were no major time breaks within the Whakamaru, and there are distinct geochemical changes before and after. Now I want to know, what are the storage depths of the magma bodies? For the storage depths, this is where we turn to rhyolite melts, and that can help us determine the pre-eruptive storage pressures. And so what we do is that, looking at different minerals, we look for the pressure at which melt of a given composition is in equilibrium with a specified mineral assemblage. Here I have mineral 1, 2, and 3, and I want to emphasize that we want to think of the minerals 1, 2, and 3 as being in equilibrium with the glass of this composition. So we input the glass that I measured with major elements and search in temperature and pressure space to try to find the storage pressure. So we explore different mineral assemblages to determine which geobarometer to use. The reason that we do this is because we are unable to directly observe the assemblage for each lapillus due to their small size, just because they're small lapilli. We consider the assemblages resulting from melts calculations as a proxy for the expected assemblages in each lapillus. And so the different minerals that we considered are quartz, plagioclase, sanidine, and orthopyroxene. And this will hopefully help to confirm the mineralogy that we see in the horizons. But since we expect the Kohiawa yellow to have sanidine and the green Kohiawa not to have sanidine, this is where we can employ rhyolite melts. All right, so when I say exploring pressure space, I'm looking at plage, quartz, sanidine, and orthopyroxene. The way that sort of the melts output would look is looking in temperature and pressure space. How do you say this? Like a junction like this. Intersection, that's the word. An intersection like this would yield a quartz plus plage plus sanidine pressure. An intersection like this, notice it's just the plagioclase and quartz. And so you would say that quartz and plagioclase are in equilibrium with the melt composition that you chose, but you would say that orthopyroxene and sanidine in this case are not in equilibrium. Similarly, here you could have a quartz plus plage plus OPX. And here you would have quartz plus plage plus sanidine plus OPX. And so here are sort of the different sort of pressure spaces that we're exploring in order to try to find out the storage pressures of these different compositions. Okay, yeah. Oops. All right, and so here, so what I did was run the mean compositions through rhyolite melts. And what I found here is that here's storage pressure on the y-axis and calcium on the x-axis. And this is looking through storage pressure for all of the different lapilli. And what you can see here is that this bar at 125 megapascals is the typical Taupo Volcanic Zone pressure. Here you can see that both the Kohiawa yellow and the Kohiawa green have storage pressures of approximately 85 to 150 megapascals. So it's all fairly shallow and all very consistently shallow storage pressures. And then we have the Pyrata over here in the blue that has fairly shallow, but also has a few compositions that are slightly deeper storage pressures. And then the Murapara has one shallow storage pressure that overlaps sort of the 100 to 150 MPa range, and then also has a deeper signature, this 200 to 250 megapascal range. And as I said before, this orange is typical TVZ depths. This is from Galda et al. 2018. Looking here, here's just preliminary data that they had for Whakamaru ignimbrites, and you can see that this overlaps fairly well. But then note that through the subsequent crustal ladder eruptions, it seems to be this sort of deepening and then shallowing trend. And so what we see here is that we have the shallow Whakamaru, and then we might see the start of this deepening trend with just the post-Whakamaru magmas here. And again, similarly to Begway's Begu, I'm not actually trying to pronounce Flo's last name, but Flo's work here also shows fairly shallow magma bodies. And now looking, this is all storage pressures, and I also want to show you the different sort of pressure spaces that we looked at. And so the vast majority of the compositions that we ran saturated in quartz plus plagioclase. And so this is just sort of the two mineral assemblage. And note up here that these are the ones, these ones at the 0 are the compositions that did not saturate in quartz plus plagioclase. But note that the vast majority of the pre-Whakamaru, the Pyrata, and then the post-Whakamaru out here are quartz plus plag, and most of the green as well. But conspicuously, the quartz plus plag plus sanidine pressures seem to favor sort of these yellow, Kohiawa yellow compositions. And so, excitingly, at least the two magma bodies that fed the Whakamaru eruptions, the Kohiawa yellow, rhyolite melts models it to be sanidine bearing, and also that Kohiawa green does not have sanidine. And so we can sort of use rhyolite melts to confirm the geochemistry and also to sort of confirm the mineralogy that would be able to see in the different horizons. Importantly, since we can't look at the mineralogy of the individual lapilli, and looking at the mineralogy of the individual horizon, in most of the horizons, you would be able to see sanidine. And so you could assume that most of the magmas, that all of the magmas have sanidine. However, this confirms that, that just the Kohiawa yellow should have sanidine, whereas the Kohiawa green likely does not. Another thing is that both magmas stored at 100 to 150 megapascals, which is fairly shallow, but fairly typical for the Taupo Volcanic Zone. And now I want to know, finally, how do the number and depths of magma bodies change through the life cycle of a large magmatic system? So this is sort of pulling it all together. I'm now looking, sorry, you're going to have to, if you're used to looking at pressure on the y-axis, just like tilt your head like this, because now we're looking at horizon here on the y versus storage along the x-axis. And so you can see here that the Kohiawa magma storage pressures are consistent through the eruptions. And you can also see again that both the green and the yellow are erupting throughout the system. But what's quite interesting is that in the Pyrata, there seem to be a few horizons that are slightly deeper, and so it seems to be some sort of I guess controlled via like the timing of the eruption. And again, up here in the post-Whakamaru, up in the Murapara Banish, you have at first a shallow signature before it dives deeper to a deeper storage signature. And I will say another thing is that there are distinct compositional differences after the paleosols, but what I find quite interesting is that it seems that just before and after the paleosols, although there are compositional differences, it seems to be that the pressure sort of, the thing that's just erupted seems to sort of mirror the pressure that was just before. And again, yeah, the two groups here, just to remind you of the different magmas. And so the magma story thus far. Now, in addition to just showing the two different bodies, we can also look at it through time, or excuse me, in pressure space. And so the shallow magma storage is consistent for both magma types, and both types erupted through the Whakamaru eruptions. And here, again, we have a few signatures now with sanidine being added to the Kohiawa yellow. And so this is sort of pulling it all together. This is what we see through time. We have the Pyrata erupting somewhere between about 100 and 200 megapascals. And then we have the Kohiawa yellow and green with different signatures erupting together. And then finally, we have the Murapara Banish on top. And this is what sort of the whole magma crust looks like, but obviously through time, I don't think that all of them are there at the same time. It is unclear how the magma bodies are organized sort of in map view. We can see the sort of the third dimension, but we don't necessarily, and the fourth dimension. So we can see the third and fourth dimension, but not the first and the second. Unknown how large the magma bodies are, so unsure exactly how large the volumes are. And it's unknown which magma type fed which Whakamaru ignimbrite. And so sort of the first difficult part of trying to figure out which ignimbrite goes with which magma body is still unclear. But we'll get there. And so just to finish, the distribution of magma in the crust, there are two magma types that erupt repeatedly for the Whakamaru system. There's one predominant storage pressure, and then for both before and after the Whakamaru, there are different storage and compositional groups. And then looking at it through time, magmas consistently erupt from shallow storage for the Whakamaru eruptions. And then it does go distinctly deeper just after, despite having just sort of like these little bridges of very similar pressures in the first thing erupted. And then the Kohiawa tephras show the coexistence of two large magma bodies through the Whakamaru system, which really helps sort of put the whole reservoir in perspective, that there is even the ability for the crust to have two magma bodies there at the same time. And so ignimbrites are to follow. Would like to link the tephra and the ignimbrites. I have about 30 pumice clasts from the ignimbrites that I've done the major and trace elements on, but stay tuned for the next talk. And hopefully we'll be able to use that to look at the distal Rangitawa tephra, or excuse me, the distal, be able to link the distal tephra and the Whakamaru ignimbrites using this tephra, and then also hopefully fingerprinting the ignimbrites for the rest of the PhD. And so I'll leave you here with the main conclusions that I had from the previous slide. And now I'm happy to take questions.
Thank you, Lydia. That was great. Yes, we have time for questions and discussion. So if you'd like to raise your hand and unmute yourself, it's fine to do that. Or if you'd like, you can do a chat question and I'll just read it for folks. And then maybe to give some folks a little bit of time, I had one question, Lydia. And I know, many of these eruptions initiate with phreatic interaction. I was wondering if you could see that in any of your sections.
Like phreatum, like the sort of like the explosive stuff. I don't see that in any of mine. A few things that I do see, some from like the volcanological perspective, is that there are like a few very minor crossbeds. And so one of the interpretations is that these are deposited in a lagoonal setting. And so so no, I don't see any phreatic stuff, but you do see fairly distinct trends in grain size. So that does vary quite a bit, sort of, but never gets bigger than maybe a centimeter across.
Okay, thanks. And Kathy Cashman has a question, and she writes, to what extent are the differences between the green and yellow explained by temperature?
To what extent are the green and yellow just explained? Oh, with the zircon saturation temperature? Yeah, here, let me go back to my zircon saturation temperature. I will say,
also thinking just the sanidine versus not sanidine.
Oh yeah, so the difference in temperature, so both of them should be at the quartz feldspar cotectic, since we have plage and quartz in both the green and the yellow, but with the quartz and plage and sanidine yellow magma, that should be probably more constrained in terms of temperature space. In terms of the zircon saturation temperature, I'm not sure if they're saturated in yellow. I was having a conversation with Calvin and Gil about this. Basically, we're using the zircon saturation temperature right now in order just to distinguish the two magma groups, but there's still a bit of a discussion on whether both of them are zircon saturated. And Calvin and Gil also have different ideas about that.
Okay, yeah, I was just struck by the sanidine versus no sanidine.
Oh, the difference in temperature?
Yeah.
Yeah, huge difference in temperature. And realistically, hang on, let me try to find the zircon saturation. Let me pull this a little bit bigger, because the zircon saturation temperatures for the yellow are quite low and look sort of like almost anomalously low, especially at such a low pressure. And so another thing that could impact that would be water. And although we think these magmas are water saturated, it might be that the activity of water could be less than 1. So there are a few factors that are still at play there.
Thanks, Lydia. It looks like we have a number of questions here. What I'm going to try to do is interleave the chat questions with the raise a hand questions. So Brenna, why don't you give the next question?
Yeah, I thank you. That was a really cool talk. I loved how you put the story together. I had a question more from a melts point of view, since I'm not familiar with it. Right, with rhyolite melts. I'm not familiar with using that particular program. Mm-hmm. And I wasn't sure, since the Kohiawa yellow seems to have both a added sanidine pressure and then a pressure that was more able to be modeled without sanidine. I wasn't sure how you had those two disparate sets when you didn't run melts on each individual lapillus. You only ran it on the whole horizon, correct?
Oh, no, sorry. No, I did. No, I ran, sorry, that if that wasn't clear. No, I did run rhyolite melts on each individual lapillus. And data that I didn't present here, I actually also ran it on individual analyses. And so overwhelmingly, let's see, this pressure. Oh, no, not that one. And so overwhelmingly, the Kohiawa yellow produces quartz plus 2 feldspar.
Okay.
Quartz plus 2 plays insanidine. Pressure estimates. However,
Okay.
there are a few here just in the quartz plus plagioclase, and that's simply because for the intersections, oftentimes we're looking. They could be, just sort of just off of the intersection. Right, rhyolite melts is fairly sensitive to composition, and so these could be very close to quartz plagioclase sanidine saturation, but just maybe off by 6 or 10 degrees.
Okay, thank you very much.
Mm-hmm.
Next question will go to the chat, and this is a question from Carrie Cooper.
Mm-hmm.
And it looked like the first and last of the Kohiawa tephra horizons each had only one magma type. Do you think that sampling or a real difference implying that one magma body started erupting first?
Yeah, Carrie, a great question. Yeah, we were talking about this we've been talking about this for a few weeks as well. So one of my next tasks is to go and pick another 10 or so lapilli from both the first and the last Kohiawa to see if it's a sampling error or to see if it is actually that the green started erupting first and then the yellow was the last out. I think both of them are pretty reasonable hypotheses, and it's just going to be another probably 10 or 15 lapilli before we have an answer. But sorry, I do want to emphasize, I know I have questions, but I do want to emphasize that there is just a slight change as you, where is it? Just a slight change as you go through time, just at the very last, where is it? Where's the horizons? Oh, it's through my, sorry, it's on my other side. Yeah, just that you do have this slight difference in chemistry towards the very top of the Kohiawa, and I think that could be pretty cool to look at as well with more lapilli.
Thanks, Lydia. And I should say, if the folks with the chat questions have follow-up, feel free to unmute yourself. That's fine too. Okay, so I guess we'll go on to Montse. Thank you.
Hi, thanks for a wonderful talk. I was wondering at the beginning in the geological map, it seems that the storage moved like in space, like not like space, like on the, yeah, like there. It seems like it moved, right? From maybe north to south or south to, do you think that have?
Sorry, yeah.
Do you think that has an influence in the storage? Like, do the magma body also change from like north to south or south to west?
I think there's a possibility there, and there is definitely sort of a slightly northward trend later on in the flare-up zone, in the flare-up. But I think for the Whakamaru, I think that the caldera would likely be where the magma bodies were stored, but I think that's still needs a bit of thinking as well. One thing to note though is that this is such an active volcanic area. Looking at the different overlaps of the different ignimbrites can be quite challenging, and even the Whakamaru caldera, it's not particularly obvious today, just because there's been so much, successive volcanism, including Lake Taupo, which was the caldera of the last major super eruption on Earth. And so it is quite difficult, but to determine that. But yes, the later flare-up stuff did come from slightly north. So yes, interesting.
All right, we have one more chat question from Jake Jordan. And Jake writes, is there any smoking gun or definitive reason that the green and the yellow can't be from one poorly mixed body?
Oh, for the poorly mixed body, I think really that we just see it's just such distinct chemical differences between them in so many different spaces. One thing I didn't mention in the talk is that not only did I look at these bivariate plots, but I also did a Euclidean distance calculation to try to sort of measure basically like the multi-component hypotenuse between all the different lapilli. And really the lapilli, there's just not a lot of overlap between them. So I guess you could have them, but I don't think so. I think it's pretty clear that one was sanidine bearing and slightly different to the other one. I will say though that I think as far as like this, like as far as like where the actual magmas come from, this is sort of waxing poetic a bit. So someone can tell me to stop. But I do think that they're fairly similar in that they could potentially be coming from the same source, and just that one fractionated more plagically than sanidine than the other. And so that the melt was slightly more evolved. I don't think that has an implication on one being more evolved during like going from basically being extracted to storage. I don't think that has a bearing on that, but I do think that they're distinct magma bodies. If someone disagrees, I'd love to hear another option.
Thanks. It looks like we've gone through the chat and the other questions. Lydia, I had one question. I don't know if this applies to your work or if other folks are working on this. Are there good constraints on the volatile contents of these units? Of
the volatile contents?
Yeah.
I'm not. So at this pressure and with high silica rhyolites, you would think that they would be water saturated. And so I think that it would be pretty challenging to get such shallow magmas at such high silica contents to be undersaturated. But as far as H2O, CO2, I'd have to double check or something like that.
Right. I'm not sure. I guess you could have some melt inclusions in some of the quartz. But...
Yeah, there are melt inclusions. Yeah, and the quartz are really big. So I'll have to double check. I don't have that on the tip of my tongue.
Are there any other questions for? Well, what we usually do, Lydia, if you have a couple minutes, is we'll let everybody go that needs to, but we might stick around for a couple minutes. There always are a few questions that people have that they like to ask in the small.
Yeah, absolutely. Thanks, everybody.
Yeah, thanks, everybody. Yeah, thanks for joining us on Election Day, and go vote, as Lydia says, if you haven't, for the US folks. Anybody else who can vote, you should vote too. All right, see everybody next week. That was great, Lydia. That was fantastic.
Oh, thank you. Yeah, that was really fun. It's kind of strange just presenting to my kitchen, but lots of fun.
I know that's a common thing. It seems